Okay.
see how they're doing.
So I would do, so it would be 9 as the whole number would be the big number. And then the remainder would be 2 on top for the denominator. And then the original denominator would be 3. But I don't know if that's right.
Which problem are you working on right now?
What's that?
Which problem are you working on right now?
The 29 one.
Yeah, walk me through that.
Oh, wait. Okay, I didn't see the bottom part. My bad. So 29 over 7. Oh, okay.
Yeah, it's 29 over 7.
Got you. Okay. Hold on. Let me do this again.
Yeah, take your time. Anybody else want to lend a hand?
So how I did it is I divided 29 by 7 first, and then I got 4.14, and then I did that. I rounded that up to 4, and then I did 29 minus 28, and I got 1, and then I did after I did 7 times 4, I got 28. So 29 minus 28, and then that'll be 4, and then 1 over 7.
Yeah, that's absolutely right.
Mhm.
Yeah, because 7 goes into 29 4 times,
Mhm.
and that becomes 28. So you have 1 left over, so it'd be 1/7. Good. I'm just gonna jump into one of the other rooms and check on to see how they're doing. I'll be right back. How are you guys doing over here? We still working on this problem?
No, we're finished.
And what'd you end up getting for this problem?
4 1/7.
Sounds good. I'm gonna go ahead and close all the rooms now. I think that everybody was on the right track there. So that's good. I'm going to routinely sort of break you guys up into breakout rooms just so that you guys can have a chance to talk things out with your classmates, but also because I know it helps break out the monotony of my drone and uninteresting voice. Okay. So it also gives you an opportunity to just get in there, get your hands dirty, and work with the numbers as we go through this, so you become a little less scared, a little less timid as far as like being afraid of making a mistake. We are here to make mistakes so that we can correct them. So never be afraid to make a mistake. You will notice throughout the semester that I will routinely make mistakes. So if you see one, please call me out on those. Okay, I think that we're all back from the breakout rooms. Okay. All right. Okay. So to simplify a problem like this, as we probably have all gotten there, we're just doing simple division to write this improper fraction as a mixed number. We can just divide 7 into 29. And a lot of you guys will be able to do this in your head. 7 goes into 29 4 times. And 7 times 4 would be 28. So you would have 1 left over. And you're just going to go ahead and keep the original denominator. So this should be the answer here. But if you wanted to see it drawn out with long division, you could definitely do that as well. 29 divided by 7. Remember, we ask ourselves, how many times can 7 go into this number? Or in other words, 7 times what gives us something close to 29? So 7 times 4 would give us 28. And we're going to subtract that away. That leaves us with a remainder of 1. And remember, we're going to write our mixed numbers in the form, our whole number goes right here. This is the whole number part, because 7 goes into this 4 whole times. You're left with this remainder here. So in some sense, if we wanted to, we could say that this is the remainder over the original numerator. I'm sorry, the original denominator. Let me go ahead and try to correct that mistake. There's the first mistake of the semester. So we'll throw the remainder over the original divisor or the original denominator, and this will be our answer. Anybody have any questions about that? And so like if you wanted to locate this on the number line, 29 over 7, it's really easy to throw this into the calculator. 29, let's say 29 divided by 7, and you can get this weird decimal number. But in this class, our decimals are going to be our expression of last resort. I prefer improper fractions over decimals, right? Because this is an exact number. This one is being rounded off by the memory capacity of the calculator, right? In some, if we had a higher precision calculator, this might go on forever with different numbers behind the decimal point. So once they cut it off at 8 or so decimal values, they've cut it off, and that's just an approximation. It's not an exact value. But this is an exact value. So I would prefer you guys to write things like that as exact fractions or as mixed numbers whenever the instructions in MyLabs Plus ask you to write your answer as a mixed number. Okay, moving right along. So I want to show you guys that in some sense, fractions are like division, and they're sort of like multiplication. So what I want to do here is throw some problems at you, and let's just sort of talk through them. Because like it turns out that even though we might think of multiplication and division as more complicated operations than addition and subtraction, they're a lot easier to do with fractions. Addition and subtraction tend to be more complicated with fractions. So let's look at some multiplying and dividing. Okay. So first, I might give you 2/3 times another fraction. Maybe we cut those 2/3 into 1/2. And nobody can see this because it's super blurry. Let me go ahead and auto adjust. Boom, boom, boom. So can anybody tell me how you would go about performing this multiplication?
You just multiply across.
Yeah, absolutely. So there's a lot of times students will get confused and say, like, don't we have to get common denominators because they vaguely remember something about common denominators from their grade school math classes. But with multiplying fractions, you don't have to worry about common denominators at all. We're going to get 2 times 1 is 2. 3 times 2 is 6. Okay. I'm going to leave this alone for now. Some of you might be thinking, don't we need to reduce this fraction or simplify the fraction? Yes, but I want to go in depth into what simplifying a fraction actually means here a little later on. Okay, so this wouldn't be the final answer for a problem like this, but for now, we're just going to leave it alone. Okay, let's look at another one. Maybe 8/9 times 5/7. Anybody tell me what this one is? And don't worry about reducing it or simplifying the fraction. Just
40 over 63.
Yeah. 8 times 5 is 40. 9 times 7 is 63. You guys okay with that? Any questions? So at this point, when we're doing these operations, I think that it's hard, we lose track of how we're supposed to be interpreting the multiplication, right? Like in some sense, if I were to tell you, let's multiply 8 times, let's just do 8 times 5, right? We know that that one was 40. That 8 times a number becomes a bigger number. But if we had 8/9, I'm not sure where that is on the number line, not just looking at it. I don't know exactly where 5/7 is on the number line. And I sure as hell don't know where 40 over 63 is on the number line, right? These numbers are getting harder to interpret right out the gate. I know where 8 is on the number line. And when I multiply that by 5, which I know its location on the number line, when I multiply these together, they become a bigger number. But I don't know what the size or location of these fractions are. So that's one way that students sort of lose track of or have confusion or apprehension about fractions, right? Because it takes a little bit more work to interpret their size and their location. But for our purposes, the algorithm, the process that you need to follow when you're multiplying two fractions is just multiply the tops, multiply the bottoms, and you'll be good to go. We'll figure out how to simplify this later on, okay? We don't have to complicate our lives right now. What you could say is that 8 is almost as big as 9. So this has to be sort of close to 1, right? Because if I were to take the number line between 0 and 1, and I were to divide this into 9 equal spaces, so 1, that's 3 spaces, and then I divide it into 3 more, so 3 spaces there, 3 spaces there, 3 spaces there. So now I have 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces. So 8/9 would be this one right here, 8/9. So it's pretty close to 1. 5/7, if I did that same thing, so this is like our 8/9 here, 0 and 1. This time we're going to cut this space into 7 equal pieces, which is going to be harder for me to do, so bear with me. This isn't going to be perfect. That means I need 6 tick marks. So 1, 2, 3, 4, 5, 6. So we have 1, 2, 3, 4, 5, 6, 7 even spaces. So you could say this is 1/7, 2/7, 3/7, 4/7, 5/7. And that's a little bit further away from 1, still kind of close to 1. And there's no way I'm going to do this one, all right? I'm not going to take 0, the interval between 0 and 1, and divide it into 63 even spaces. But that's sort of what we're doing without thinking about it. We're taking this number 8/9, which is sort of close to 1, a little bit smaller than 1. 8 divided by 9 is 0.888, right? So we could say that this is 0.8889. And we're multiplying that by 5/7 would be 5 divided by 7, which I'm just going to round this off to 4 decimal places, 7143. And then taking these numbers and multiplying them. So let me go ahead and do that. 0.8889 times, let me go ahead and erase this actually, so you have, it's a little bit clearer. 0.8889 times 0.7143, and we get about, when we multiply those, we got about 0.6349. So somehow 40 over 63 has to be close to this decimal representation. So 40 divided by 63, kind of close. Right? We have the same decimal number, 6349, 6349. And then things sort of are a little bit different as you trail off. But it would be good enough for government work, right? Just sort of like an estimation practice. You don't have to be able to do what I just did right here. I just want to show you that you should be a little bit playful with these numbers, right? You should be able to check yourself before you wreck yourself to see that, like, okay, if I'm doing this correctly, then my decimal representations should be pretty close to each other when I check those in the calculator. Or you could be very devil may care and just say, okay, Mr. Aguilar just said multiply the tops, multiply the bottoms. That'll be good enough for government work. No need complicating your lives. So I just want to show you that. Does anybody know, we've already seen this earlier in class today in the lecture, but if I had, let's say 100 times 1/5. Does anybody know how to perform that multiplication when we have a whole number and a fraction?
You would
Don't you put a 1 over the 100?
Yeah.
You put a 1 over the 100 or you put a 1 under the 100?
Under.
Oh, damn.
Yeah, yeah.
Under.
So that's definitely one strategy, right? We can go ahead and write this as 100 over 1. Remember that 100 divided by 1 is still 100. So these are the same value, they just look different. But now that we have a fraction, we can just perform that operation where we multiply the tops, multiply the bottoms, and you have 100 over 5. Does anybody know what 1/5 of 100 is? Like if you had a $100 bill and you wanted a fifth of that.
20.
I think I heard somebody say it.
20.
20. Well, that makes sense because 100, if we interpret this fraction 100 over 5 as a division problem, this would be the same thing as 100 divided by 5. And that would be 20. Okay, so we're approaching this idea of simplifying our fractions a little bit. I still want to hold off because I want to talk about dividing fractions real quick. So let me see, we did 2 problems on the other side, so this had to have been 3. Let's look at a 4th problem. How about 5/8 divided by 1/2. Does anybody know how you would go about doing this division problem?
You have to find the common denominator.
No, actually with multiplication and
that?
division, you don't need a common denominator at all.
Okay.
Cross multiply.
I think
when
you
you
had
say-
to do cross.
Where you do what?
I think you had to do like a cross, like multiply 5 times 2, and then put it in the top, and then 8 times 1, and then put it as a denominator.
Okay, I see what you're saying.
Something like that. I don't remember.
Yeah, it's something like that. I think that
Isn't the second fraction flip?
yeah, so that's the way I'm going to teach you guys. So I've seen people do this cross multiplication. I really don't like the phrase cross multiplication because I think it does more harm than good. It turns out that division is just multiplication by some reciprocal. So what does that even mean? Let me throw some vocabulary at you real quick. Reciprocal is basically, if you think about a number multiplied by its reciprocal gives the result of 1. Okay, I think that's a little bit strange, but let's table this for a second. Let's hold this off. Let's think about something like 3 times some number gives you 1. Can anybody tell me what this number is?
1.
3 times 1 gives you 1? Well, 3 times some number is going to put us back at 1 somehow, but it's not going to be 1. But we need to figure out what this number is, because 3 has a reciprocal, and if we multiply 3 by its reciprocal, we'll get back to 1. Does anybody have any guesses?
Is it -3?
Well,
1/3.
Somebody said it. So we have
1/3.
some ideas here, right? These are our candidates. We know that 3 times 1 won't work because that's equal to 3. Right, so 1 doesn't work. I think somebody said 3 times -3. And it turns out that that's -9. So that one won't work either. But I think somebody else said it.
Like 1/3. I'm not sure.
3 times 1/3. And yeah, it turns out that that's equal to 1. But I mean, you can probably see this pattern where we're going here. I think that an easier way of thinking of this is maybe if I had asked you 3 divided by something gives you 1. What would that something be?
Three.
Yeah. In that case, 3 works. And we can think of division as being taking that 3 and cutting it up into 3 pieces. So like if you had 3 cookies and you wanted to share that with 3 friends, each friend, which is here by the purple square, gets how many cookies? This friend gets 1 cookie. The pink circles are the cookies. I'll put little dots so they're chocolate chips. Right, but I've divided 3 cookies among 3 friends, and each of those friends gets 1 cookie. So when we think about division, it's sort of a little bit easier to think of a number divided by itself gives us 1. But a number times something becoming smaller, that's harder to think about. And it turns out that if you multiply 3 times a fraction, where you just take 3 and sort of flip it to 1/3, that this is what we're going to call the reciprocal of 3. So 3 times its reciprocal gives you 1. And this will make sense here once we sort of like lay it all out. So continued. 3 times 1/3. If we try to figure this out, we said we need to rewrite this as take the 3, write it as 3 over 1, and then multiply it by 1/3. Well, now we're just multiplying fractions, or 2 different fractions, and we get 3 over 3, because 3 times 1 is 3. 1 times 3 is also 3. And then if we interpret this as a division problem, 3 divided by itself is just 1.
Division.
So if I asked you, what is 5 times 1/5, you should be able to identify that these guys are reciprocals. And when you multiply reciprocals without thinking about it, you should just get 1. But when you do think a little bit about it, you'll think to yourself, this is really 5 divided by 5. Like the number down here in the fraction is what you're using in the division to perform this operation. So in some sense, 5 times 1/5 is the same as 5 divided by 5. And it turns out you can go both ways with this. So I want to introduce this idea that when you're dividing a fraction, or even if you're multiplying fractions, but usually we use it in the context with division with fractions. This is what you need to remember. You need to remember to keep, switch, flip. That is, keep the first fraction, switch to the opposite operation, switch to multiplication, and then flip the second fraction to its reciprocal. So in that concrete example, we were looking at 5/8 divided by 1/2. What we're going to do is keep, switch, flip. So I'm going to keep 5/8. I'm going to switch to multiplication. And I'm going to flip this to 2/1. So I should be getting 10/8. And we won't worry about reducing that or simplifying it right now. Does anybody have any questions? Okay. So what I want to do is give you guys some practice problems. Maybe 3 of them. You could work in breakout rooms. So you try. So we'll do 1/7 times 8/9. 3/2 divided by 4/5. 20/30 times, let's do 8/7. I'll give you one more just to even this out a little bit. 5 divided by 1/7. Okay. And we probably can't see all of these. There we go. Okay, so take a moment to write these down real quick.
What's the last one?
The last one is 5 divided by 1/7.
Okay.
Okay, so just to repeat these, the first one is 1/7 times 8/9. Second one is 3/2 divided by 4/5. Third one is 20/30 times 8/7. And then the last one is 5 divided by 1/7. So what I'm going to do is throw you guys in breakout rooms again, so you can work among your classmates, and maybe I'll make the breakout rooms slightly larger. Yeah, let's do 3 breakout rooms. All right, I will check in on you in just a second. Remember, you have to accept the breakout room invitation. There we go. How are you guys doing in here?
We got them.
Good.
All 4 of them?
Yep, all 4 of them.
Awesome. Anybody else have any questions?
No.
Okay, I'm gonna go check on one of the other rooms.
Okay.
You guys are doing great. Keep it up. How's it going in this room?
We're done.
Good.
Are there any questions, comments, or concerns, or are we pretty much done with these?
Well, I think we're done. We didn't have to simplify, right?
No.
Okay.
Well, then we're good.
Okay,
we're good.
cool. I will check on the last room, and then I will ask you guys to rejoin the main room. How are we doing over here?
Good.
Are we just about complete with these, or are there any questions, comments, or concerns that you guys need me to address? Okay.
We pretty much went over like every problem, so and we got the same answer.
Awesome. Yeah, and you didn't have to worry about reducing here or simplifying the fractions because that's the last thing I want to touch on today, simplifying fractions. So I'll go ahead and close all the breakout rooms now. So we're going to all join the main room Zoom session here in a second. I sort of get the sense that these, I think that for a lot of you, these little problem sets that I'm throwing together are very easy right now. Is that the feeling that you guys are having?
I am at this moment, but it wasn't always like that. It was the way you explained it. So
okay. Yeah, I'm glad that we're having the chance to get this practice in, because fractions don't have to be this thing that is like super intimidating. Okay. So my expectation or my assumption is that the way you guys went about working these, at least for multiplying, this first one's pretty straightforward. I think I think we already did 7 times 9 in a previous problem, so that's 63, and we should have 8 on top. Is everybody good with that one? Let me go ahead
Yes.
and figure out where I am. Boom. Okay, so that one's good, and it turns out that one, if I'm just looking at it, doesn't look like it can be reduced, but we'll talk about simplifying fractions in a little bit. Here, what I would go ahead and do is just rewrite this problem as 3/2 times 5/4. And then we can just do a straight up multiplication, multiplying straight across, so that we have 3 times 5 is 15, 2 times 4 is 8, and that'll be the end of that. You don't have to sort of worry and wonder, am I done? We'll get to the point where we ask ourselves, is this the most I can do, or am I just done? This one does not look like it can be reduced, and we haven't even talked about reducing fractions, so on to the next one. So again, multiplication just means we're going straight across. This is going to be 8 times 2 would be 16 with a 0 in the back. 7 times 3 would be 21 with the 0 in the back. So we could leave it at that because again, we're not worrying about simplifying the fraction just yet. Is everybody okay with the third one?
Yes.
Okay,
Yeah.
and then this one, now if you wanted to, you can change the 5 into 5/1 so that we have consistent fractions across the board. But since we're just gonna divide this and we know keep, switch, flip, I'm gonna go ahead and keep this number the same, change to multiplication, and flip this to its reciprocal, which would be 7/1 or just plain 7. So 5 times 7 should just be 35. So that'll be our answer there. Does anybody have any questions, comments, or concerns? Or is this what everybody got? Cool. And let me ask you a different way. Did anybody get something different or run into any like roadblocks? Awesome. Okay. We're on our way. One thing that you'll run into in your homework assignments in MyLabs Plus is they will ask you to do some operations with mixed numbers and fractions. So one thing I haven't talked about yet, but I might as well just expose you to it. If we had that 1.5 cup recipe, whatever that was, sugar, flour, it doesn't really matter at this point. And we wanted to multiply that by 7/8. How would we go about doing that when we have a fraction and a mixed number? Well, we just want to be consistent. So I really can't do anything with this until I have this mixed number converted into a fraction, into either a proper or an improper fraction. So I want to show you how to convert mixed numbers into fractions. And we already took improper fractions and converted them into mixed numbers using division. So if we're going the opposite direction from a mixed number to a fraction, you might think it feels natural that we would have to multiply something, right? Like for instance, when we got 1.5, we said 3/2 can be written as 3 divided by 2. When you do that division, you get 1 times 2, and you subtract the 2 and get a remainder of 1. So we get a whole number of 1, and then the remainder of 1/2. But in this process, we did division and we did subtraction. So
I can't really see your paper and I kind of got lost. Can you start back over on that?
yeah, let me go ahead and
Sorry.
do that. So what I'm saying here is we're going to have to be able to multiply mixed numbers times fractions, right? But in order to do that, we want to have everything as fractions across the board. So we want to take our mixed numbers and convert them into fractions. Well, when we were going from an improper fraction to a mixed number, we use division and we use subtraction. Okay. But now, if we want to go from a mixed number to a fraction, you might think, okay, well, we're doing the opposite of what we did here, so maybe we're going to use multiplication and addition. Does that feel like it should make sense? We're just reversing the operation to go in the opposite direction. So if I have 1 and 1/2, what I'll do is multiply the denominator here 2 times the whole number, and then I'll take whatever that is, that result, and add it to whatever's on top, whatever's in the numerator. So you could think about this like 2 times 1, where 2 times 1 is the denominator times the whole number part, and then you add that to whatever's up here, which is the 1, and you just keep it over the original denominator, which is 2. So what we should be getting, 2 times 1 is 2, plus 1 is 3, so we should have 3, and then keep the original denominator. Does that make sense, or are there any questions?
It makes sense.
So if I wanted to complete this problem up here, I have to rewrite it as 3 over 2 times 7 over 8, which is then a straightforward multiplication problem. 3 times 7 is 21, 2 times 8 is 16, and we'll just call it a day. Okay. So there's 2 topics left that I want to cover today. That is adding and subtracting fractions, and then simplifying fractions. But what I first want to do is the simplifying fractions part. I think that's going to be super crucial here and really useful for us when we get to adding and subtracting fractions. Is it still difficult to see this when I'm zoomed out?
I can see it.
Okay. So when we talked about fractions at the beginning of this lecture, I called them rational numbers. And they're written in the form n over d, where n is the numerator, d is the denominator. In some sense, you could think about this number on top being divided by the one on the bottom. But now I sort of want to introduce you guys to this idea of prime versus composite numbers. And I guarantee you, or I promise you, I'm not complicating your life for no reason. this idea of identifying prime numbers versus composite numbers and breaking down composite numbers is going to be super useful throughout the semester. Okay, does anybody know what a prime number is?
Something that can't go into itself to make a number or something like that.
Yeah, we're really close to that definition. Whenever we have numbers, we can think about numbers as being made up of other numbers. For instance, let me give you this example, right? 20 can be written as, and usually I like to do a factor chart here. As a T-chart, I can think of two numbers that multiply to give me 20. Or a factor pair.
4 times 5.
Yeah, exactly. So whenever I say factor pair, I'm talking about two numbers that multiply to make another number. And you can think of multiple factors for 20. Somebody said 4 times 5. The easiest one is always 1 times itself. 2 times 10. And then finally 4 times 5. So it turns out that in this factor chart for the number 20, 20 can be represented in 3 ways by multiplication. We could say that 1 times 20 is 20, 2 times 10 is 20, 4 times 5 is 20. So we would say that this has 3 factor pairs. But some numbers, let's think about 17. Can anybody think of factor pairs that multiply to make 17?
Just be 1 and 17.
1 and 17. Are there any other factor pairs? And when I say factor pairs, I mean specifically they have to be whole numbers.
No.
No. So what you would say is that there's only one factor pair here. And because 17 can only be written in terms of 1 and itself, we would say that this is a prime number. Whereas 20, because it has 3 factor pairs, is a composite number. So in some sense, a composite number is a number that can be made up of multiple numbers other than 1 in itself. And when we say making them up, we mean like building them up through multiplication. Okay. So it's super useful to have some prime numbers memorized. So let me give you a list of primes. So our prime numbers are going to be 2, 3, 5, 7, 11, 13, 17, 19, 20 is not 1, 21 is not 1, 22 is not 1, 23, And it's pretty much just useful to memorize maybe the first handful of primes. And now you might be wondering, okay, why is he making us memorize these primes? And then I guess the answer to that rhetorical question that I posed to myself is that I'm not making you memorize them. It's just super useful to have them, a few of them memorized. And the reason why it's useful is because we're going to use this idea of prime factors to simplify our fractions. So we're going to simplify, or simplifying fractions is made super easy by breaking down the numerator and the denominator into their prime factors. Okay, so that is if your numerator or denominator are prime, I'm sorry, if they're composite numbers, then we can break them down into their factors, specifically their prime factors, and then we can do some really awesome stuff with that, okay? If we remember that fractions in some sense are division problems, okay? So a lot of times when you run across fractions in life, it turns out that even though fractions may look different, you might be given two fractions that look different on the surface, they actually have the same value. So for instance, if I asked you which one of these is bigger, 1/2 or 50 over 100, which one do you think is bigger? Or which one has a greater value?
Are the
The second
same?
one?
Same.
Okay, so we're saying some people think that we have the same. Is there anybody thinking that one of these is bigger than the other?
Same.
Okay, everybody seems to believe that they're the same. Can anybody tell me why they're the same value though?
Half of 100 is 50.
Yeah, that is true. These are equal because half of 100 is 50 and half of 2 is 1. So then why on God's green earth will we write these fractions differently, right? Or if I asked you, can I write this as 36 over 72? Does this have the same value as these?
Yes.
Why?
Because 36 is half of 72.
Yeah, and I could play that game all day, right? Like I could come up with some number, 200 over 400. I'm just choosing easy ones now because I'm a little lazy. This has the same value as this, and this, and this. But we would say that even though these all have the same value, this fraction is written in lowest terms. All of them have the same value. Again, going back to thinking about fractions as a part over a whole. 1 part of 2 is half of that whole. 50 out of 100 is half of that total amount. 36 over 72, or 36 out of 72 is half of that total amount. So rather than talk about 200 over 400, it's just a lot more simple to say, well, this is just half. But not all of these fractions that we're going to encounter are going to be super easy to like determine whether or not, you know, we can simplify that just by looking at it. Okay, so let me think about a problem. Let's do some multiplication. What if I said, let's multiply 10 over 5 times 35 over 20. what should I get here?
$350 over 100.
350 over 100. Does anybody know how I would go about simplifying this? Or does anybody know how to go about simplifying that? Can it be simplified?
Pick a number that goes into both of them, like 10. Start
Yeah.
there.
Yeah, like that's the traditional method that we're used to being taught from grade school, maybe, where we take a number and we divide it out of both the top and the bottom. But a lot of times we don't know why we're doing that. And I think that it makes a lot more sense to go ahead and use this idea of prime factorization. That is, what I'm going to do here is I'm going to take 350 and I'm going to start breaking this down into smaller and smaller numbers. I'm also going to do that with 100. Okay. And I'm going to do what's called a prime factor tree to help me break down these numbers into smaller, more manageable numbers. Because once these become super large, it's hard to determine, can we simplify it further? Because maybe we choose to divide these by 10 and by 5 and then by 5 again, maybe. If these are large numbers, sometimes it's hard to determine when do we stop. Okay, so let me go ahead and say, okay, 350, we used 10 times 35 to multiply those out. Okay, so in some sense, 10 times 35 is 350. Can I break down these numbers further into two numbers that multiply, or two factors that multiply to make 10? Well, I could do
5 times 2.
Yeah, 2 times 5. Can I break down 2 any further?
1 times 2.
1 times 2, yes. But because that's a prime, we're going to say that the prime numbers make up all of the other numbers. So they're the essential basic building blocks. So once we get to a prime number, I'm just going to circle it, because we're going to say we can't break that down any further, because it wouldn't help us to break it down into 2 times 1. Because then we would break down the 2 into 2 times 1 again, and the 2 times 2 times 1 again, and it just doesn't help. So once we get a prime, go ahead and bag that up. 5 is another prime number because only 5 times 1 make 5. So I'm going to circle that. So we've completed this branch of our tree. Let's break down 35 into 5 times 7. And it turns out that these two numbers are prime as well. We can't break them down any further. 5 times 1 is the only thing that will give us 5. 1 times 7 is the only thing that will give us 7. So what we can say is that 350 is equal to 2 times 5 times 5 times 7. And if you needed that verification in the calculator, 2 times 5 times 5 times 7, 350. We would say that this is the prime factorization of 350. Now we'll do the same thing with 100. 100, you could do 2 times 50, or you could do 10 times 10. It doesn't matter how you start, as long as you break down each of the branches into their prime numbers. So I'll just do 2 times 50, and then 2 is prime. I can do 2 and 25 here. 2 is prime. And then I can do 5 times 5 here, and both of those 5s are prime. So the prime factorization of 100 is equal to 2 times 2 times 5 times 5.
And this is called prime factorization.
Yeah, prime factorization, or you could say just making prime factor trees. And again, we could do 2 times 2 times 5 times 5 in the calculator to verify that that is equal to 100. Okay, so this might seem like a lot of rigmarole for little payoff. You get faster at making these prime factor trees, and it'll be important for you guys to be flexible and quick with this scratch work here. But now what we're going to do is we wanted to reduce this fraction to simplest terms. So what I'm going to do is replace 350 over 100 by the prime factors. Okay, so 350 over 100 can be rewritten as, well, the prime factorization of 350 is 2 times 5 times 5 times 7 over 2 times 2 times 5 times 5. And since we have this written out as the product of our factors, and we know that in some sense our fractions are division problems, then any numbers that you have that match on the top and the bottom are being divided against each other. So 2 divided by 2 here is 1. So in some sense, we can say that cancels out. So 2 divided by 2 is 1, so let's cancel those. So now we have no more 2's on the top. And 5 divided by 5 is also 1, so those cancel. And 5 divided by 5 is also 1, so those cancel. So all you're left with here is 7 over 2. And that's fully simplified. There's no question of whether or not we can continue because there's no longer any common factors on the top and bottom to be canceled. So we're just canceling common prime factors by division. Remember, a number divided by itself is 1, so that's why we can just get rid of it, because then we just have a 1 times whatever's left over, and 1 times anything is just whatever that thing is. But it's easier to just think about it as these cancel out, right? That's the common way we're going to talk about them. Okay, so let me throw some problems at you guys, and we'll do them all together. I won't throw you guys into breakout rooms, just so that we can get used to simplifying the fractions. (10 over 85). 24 over 26, 140 over 260, 77 over 55. Okay. So just take a moment, maybe the next 3 to 5 minutes, and I would try to reduce these by breaking down the numerators and denominators into their prime factors using that prime factorization process. How are we doing so far, guys?
Good.
Anybody still working? I feel like those of you I can see are still working. Some of you. Okay. Let me go ahead and jump in and just work through these and show you the way I would my process would be here. Now, when you're just starting off, if you're not super familiar with these prime factor trees or prime numbers in general, you'll want to go ahead and draw these out as their prime factor trees. So we'll take 10 and 85. And 10 can be broken down into 2 times 5. And 85, here, you're okay if you have to use a calculator for some part of this. I know that 5 will go into this. So I'm going to throw a 5 here, and then I'm going to take my calculator and just say that this is 85 divided by 5. That'll give me the other number. Okay. So that's 17 there. And 17 is a prime. So what we can say is since we have 10 on the top, we should have 2 times 5 on the top and 5 times 17 on the bottom. And then the 5s will cancel. So that one should be 2 over 17. Is that what it, did anybody get something different? Now, sometimes you don't have to take it all the way down to prime factors, and sometimes you don't have to draw the prime factor tree as you start to become more competent or more confident with this process. You might say to yourself, 24 is the same thing as 4 times 6. And even though I could break these down further, we might see what we can do with that, right? So I know that 26 looks like it's 2 times 13, right? And here is where having a comfortable knowledge of your times table is going to be important. And so far, it doesn't look like these factors match. So let me go ahead and break down one or both of these factors further. 4 is the same thing as 2 times 2, and then 6 is 2 times 3. And then 2 times 13 stays the same on the bottom. So it looks like all we can do is cancel out the 2's here. And then we'll sort of like an accordion, just squeeze that all back together through multiplication. So 2 times 2 is 4, times 3 is 12, and then 13 on the bottom. Does anybody have any questions about that one? One nice trick when you're looking at number 3, as far as fractions that have zeros at the end of them, I know that 10 can be divided into both of them. So what I might do when I start this problem is say, if we divide 10 out of both of them, that's the same thing as canceling a common factor of 10. Effectively, all it's going to do is get rid of these zeros. So really, we're just working with 14 over 26. And then I can break those down into their common factors. So 2 times 7 on the top, 2 times 13 here. And then the 2's will cancel, leaving me with 7 over 13. Did anybody get something different? With this one, it's really nice. You could automatically say that there's an 11 that goes into both of those. But I noticed that sometimes students will accidentally write the wrong number down, even though they're thinking the correct thing. So just to be safe, write this as 7 times 11, 5 times 11, and then notice that the 11s will cancel out. So our final answer here is going to be 7 over 5. Does anybody have any questions about simplifying the fractions? Okay, so now that I've shown you a process of simplifying the fractions, I highly recommend you practicing this prime factorization, because again, we're going to see something, we're going to see that, but also something very similar to it, but when we get into the actual algebra part, where we're dealing with not only numbers, but numbers and variables, where we're going to be able to cancel common variable factors. And even though that sounds complicated right now, it's the same principle that we're practicing here. So it's going to be super useful for you to practice breaking numbers down and doing that acrobatics with factors. Okay, so now let's talk about adding and subtracting fractions. I feel like the easiest way to talk about them is to be about them. And that is, I'm going to throw some example problems at you. We'll talk through them. If you have questions, just go ahead and unmute yourself and ask. But let's just jump right in. There's two forms of adding and subtracting fractions, or two big categories for adding and subtracting fractions. And the first category is going to be where they have common denominators. So for this kind of problem, you're going to see something like 3/8 plus 2/8. And can anybody tell me what, if you know, before we get into it, how do I go about adding these fractions? Does anybody have any idea?
Just keep the same denominator.
Yeah.
And you add the 3 plus 2.
Yeah, exactly. Exactly. So we're just going to take, because we have common denominators, we can just add the tops, keep the bottom, right? So what you always want to do is inspect to see that it has the same denominator. And since this is the same denominator, then we can just add 3 plus 2, which gives us 5, and keep that denominator of 8. You're going to keep the common denominator. Now, some people might make the mistake of rushing through this and say, okay, maybe I just add the tops, add the bottoms, but do not do that. The way you want to think about this in a physical interpretation is, imagine that you had a pizza. And we divided that, as we did in the past, into 8 even slices. But let's say that maybe you and a friend each had a pizza, and you don't live at the same house as your friend, but for whatever reason, you're going to get your leftover pizzas from the previous night and come together and have a leftover pizza party. Because, in this economy, who can order 2 fresh pizzas? We're just doing leftovers all day, every day, So your friend has 3 slices or 3/8 of a pizza. And you have 2/8 of a pizza. And you're working with your therapist about your eating problems. But in any case, we're talking about 1/8 of a pizza. So the slices haven't changed when we add these components together. The slices are the same size. So in some sense, you could think of this bottom part as telling you the size of the pizza. And since these are both 2 pizzas that are cut into 8 slices, the slices have to be the same size. So we're going to say that in total, we have these 3 piece slices, these 2 slices. So we have 5 slices, which make up an 8 subsections of the pizza. If that makes sense. So adding fractions with common denominators and subtracting fractions with common denominators is going to be super straightforward. keep the denominator, keep that common denominator. Please do not touch those denominators. If they're the same, just do the operation with the stuff on top, okay? So let's say if this is example 1, if I threw, 45 over 100 plus 5 over 100 minus 10 over 100, just to complicate it a little bit, we have 3 numbers in the mix, but we're just going to do the same thing. The denominators are all the same. Let's keep that denominator and then just do the operations that we see up here. 45 plus 5 is 50, minus 10 is going to be 40. So this should be 40 over 100. And then, since we know how to simplify fractions now, we'll simplify this in whatever efficient manner we can. I said that if these end in 0, we can cancel those out. We have 4 over 10. And we might do some prime factorization. I'm going to go ahead and write this over here real quick. 4 over 10 is equal to 2 times 2 on top and 2 times 5 on the bottom. And I know that these 2's cancel out. So I just have 2 over 5 left over. I'm just going to draw an arrow here. I hope that makes sense. Does anybody have any questions about that one? So now that we know how to simplify fractions, I expect MyLabs Plus, your homework system, expects you to simplify the fraction at the very end. So you'll do the operation, whether it's addition, subtraction, multiplication, division, and then you'll ask yourself, can I simplify this? And one helpful method that you now know is prime factorization. Okay, let's do a couple more of these adding and subtracting problems. Nine over 16 plus 5 over 16. Five over 9 plus 1 over 9. 3 over 17 plus 14 over 17. So let's take a moment to just look at those, appreciate them, admire them, and maybe work them out. Just a few minutes. I should throw a subtraction problem in here for good measure, but it's the same. Let's do 5/20 minus 3/20, and then just to mix it up, 8/9 minus 10/9. Okay. Are you guys feeling okay about these? All right, I'm going to dive right in and just work them really quickly. Because we got to do adding and subtracting without common denominators. So, what are we doing here? We're just adding the tops, right? We're just keeping that common denominator. And then we'll see how everything shakes out. 9 plus 5 is going to be 14, right? I always think of this like you take one of them over here, that becomes a 10, and you have 4 left, so that's a 14. And then we can say, okay, this is equal to 2 times 7, and this is 2 times 8, so the 2's will cancel. So that's 7/8. Now I can stop here and say that this is 7/8, and the reason why I can stop here and don't have to break down the 8 is because I know that 7 is prime, and it's not going to have any common factors with 8. So we would say that these are mutually prime, and that's when you know you can stop as far as the simplifying process or factorization process. Over here, 5 plus 1 is 6. We're going to keep that denominator of 9. And then we can call this 2 times 3 and 3 times 3 and know that these 3's cancel. So I have 2/3. On the third problem, I intentionally made it this way so that 3 plus 14 would give us 17 over 17. And rather than doing our prime factorization and canceling out common factors, it's better to think of this as a division problem, 17 divided by 17, because that should equal 1. Some students will make the mistake of saying, oh, these factors cancel and it gives me 0. But remember, you're canceling by division. 17 divided by itself is 1, so this should be the final answer. Five minus 3 should be 2 over 20. So this will be 2 over 2 times 10. So those 2's cancel, which gives me a 1 on top because 2 divided by 2 is 1. This is 1/10. Does anybody have any questions about that one? And then finally, this one, do not flip it in your brain. I am asking you to take 8 minus 10. So 8 minus 10, it's like you don't have enough to cover this bill, right? You had $8 in your bank account and you charged $10 to your debit card. So you are now at -2 over 9. I just wanted to throw some negative numbers in there because I don't think that I've had an example with negative numbers up to this point. But they exist. They exist. Just talk to my bank. I'm just kidding. I'm a little bit more fiscally responsible than that, but I like jokes. You'll notice. You'll pick it up throughout the semester. All right. So the last thing that we need to do or talk about is, okay, what if these fractions don't have common denominators? What do we do then? Well, one thing you could do is just like go talk to the registrar and withdraw from the class and just forget about your dreams of getting through this course. Or we could just say, okay, if they don't have a common denominator, then we best go find one, right? Then we need to find the common denominator. Okay, so for instance, if I had to add 3/9 plus 2/6, maybe I want to start with something a little bit easier to draw. Okay, so I'll come back to this one. Maybe I want to add 1/2 plus 3/8. This way, I can talk about pizzas. Okay. So we know here, if I wanted to draw this picture, well, first off, one thing that you might be doing if you rush into a problem like this is you might say, okay, I need to just add the tops and add the bottoms. That's never the right move. We always have to inspect to make sure that we have a common denominator, but we don't. We do not have a common denominator. This is not the same. We are not the same. I am a Martian. I just say that because Lil Wayne was just let off by the previous president. He was given a pardon. That's just a little bit of current events for you. But anyway, these are not the same denominator. Okay. And the way you could think about this is that we need to get a common denominator, because imagine that we're in the world of leftover pizza parties. Okay. We have half of a pizza over here. You know what? I hope that after the pandemic is over, that leftover pizza parties becomes a thing. Over on this side, we have a traditional pizza that's cut into 8 slices, right? That's what the denominator tells us. But we just have 3 of these slices. So 3 of these slices. And we want to add, I'm over here dropping my pens. We have 1/8, 1/8, and 1/8. That gives us our 3/8. But then we have 1/2 over here. The only way we're going to be able to mix and match these pizzas is if we have the same denomination of slice. That is, the slices have to be the same size. So what we have to do here is take this pizza and continue cutting it so that we have 8 slices. Well, this 1/2 of the pizza constitutes or is made up of how many slices? How many 8 slices? 1,
4.
2, 3, 4. So this must be, it must be the case that 1/2 is equal to 1, 2, 3, 4 out of our 8 sliced pizza. So really what we're doing here is 4/8 plus 3/8. And now that we have a common denominator, we can have our leftover pizza party and just go to town, right? So we have a total of 7/8 there. But you're not going to want to draw pizzas every time. I think that it's just like a cute gimmick that helps drive home why we need common denominators. What I usually do when I'm going to add things that are not in denominations, where we can use the easy analogy of pizzas, is think about the denominators in terms of their prime factors. Okay. And what I mean by that is we want to leave the numerators alone. We have 3 over something plus 2 over something. I want to write 9 in terms of its prime factors. Well, I know that 9 is 3 times 3. And I know that 6 is 2 times 3. Now, if I'm just inspecting and comparing the denominators, this first denominator is missing a 2, right? So imagine I wanted to put a 2 in the front of this. I could do this. But if I multiply something in the top, I have to do the same thing in the bottom. Wait, I said that backwards. If I do that in the bottom, I have to do the same thing in the top. Now, you might ask why. And the reason why is because if 2 is on the top and on the bottom, 2 divided by 2 is 1. So really, I haven't changed the value of this fraction. Okay. And you might be wondering, okay, well, why did you know to choose 2? The truth is you can choose whatever number works. What I'm trying to do here is match the denominators. So I said that there was a 2 in this denominator. Let me throw one of those over here. I have to do that on the top and the bottom. Now I have 2 times 3 times 3 on the bottom over here, and 2 times 3 over here. I need another 3. So I'm going to throw a 3 on the bottom here and a 3 on the top there. So now the denominators match. So that common denominator, if I multiply it all together, must be something over, this is 6 times 3 would be 18. This is 6 times 3 would be 18. Well, it turns out that this is 2 times 3, which is 6, and 2 times 3, which is 6. So I'm going to go up here because I'm running out of space. We have 12 over 18, and then we can go ahead and simplify that by our normal means. These both have a 6 in common, so you might call this a 2 over 3. I'm not showing the work on that one. Sorry about that. Let's look at another one without common denominators. So we need to get common denominators only when we're adding or subtracting. So 1/4 plus 5/8. Okay, so maybe you don't like that I broke these down into their prime factors, okay? I'm gonna do it one more time, if only to mess with you, okay? And then I'll show you a different way. So 1/4 can be written as 1/2 times 2. Plus 5/8 is the same thing as 2 times 2 times 2, right? 4 times 2. So I can ask myself, what factor is missing in the denominator? Well, I'm missing a 2 over here, right? I have 3 2's down here. I need another 2. If I put a 2 down here, I have to multiply by a 2 up here. So now 2 times 2 times 2 is going to be a denominator of 8. And so 1 times 2 is 2, plus this stays the same, 5. So I get 7/8. I'm going to let that one marinate for a second. Does anybody have any questions? And I'll mute.
You're on mute.
Yeah, I was just waiting for the train to pass. Okay, we got a subtraction problem in this piece. Okay. How many of you are really not liking this matching process that I'm doing?
Me.
Okay. We got a few of you guys. Everybody else seems to enjoy it thoroughly. Yeah, so I think that it's really useful to be able to do this matching process because, like I said, when we get towards more complicated stuff using variables later in the semester, this process is going to look and feel really similar to the complicated thing we do later. So it'll be useful to talk it out and figure out, why doesn't this feel good? But for now, if you're just working with numerical expressions and there's no variables in the mix, we haven't talked about variables, but we will at some point. Again, just numbers. What you can do is multiply the denominators together and say that that's going to be the common denominator. So if I have 4 and 5 on the bottom, 4 times 5 is 20. So I need to get these to be equivalent fractions with denominators of 20. Well, how do I make a 4 become a 20? Well, I have to multiply that
By 5.
by 5 on the top and the bottom. And how do I make this 5 become a 20? Well, I got to multiply this side
By
by
4.
4 over 4. And that's the same thing I'm doing over here. I'm multiplying this side by 2 over 2 to get 8 as my denominator. Okay, it just doesn't look like something we're familiar with. Okay. But once we have this, I know that 5 times 3 is 15. I know that 3 times 4 is 12. Keep that common denominator. We worked so hard to get it. And then 15 minus 12 is 3. Okay. Let me see. Can you guys still hear me?
Yes.
Yes.
Okay. So I think that I've covered all the material that we need to get you guys started on the first 2 homeworks in MyLabs Plus. The first 2 homeworks in MyLabs Plus, let's see, assignment manager, blah, 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 main menu. You will find, if you go to MyLabs Plus, there are 2 assignments called Fractions 1 and Fractions 2, if this will load. There we go. And the way this works is that you will have to complete Fractions 1 and get at least an 80% or better in order for Fractions 2 to open up. Okay. But the material that we covered today should aid you in getting through those. It'll be good practice for you guys to get in there and work those fraction problems, make the mistakes, and it'll give you plenty of time. These are going to be due, the due date is set for Sunday at 11:59 p.m. So at night, effectively at midnight. What I've done in Canvas is I reorganized the modules here. So at the top, you can access MyLabs Plus through this link here. So that's how you'll access your homework. Just a reminder, because I know we rushed through some stuff at the end of last week. Here under Module 1, let me go ahead and close this. Under Module 1, I'm going to add this lecture video from today. And I've added some lecture notes here that if you, for whatever reason, you don't want to send me a message and you want to rummage through these lecture notes, there's handouts here that you can read that talk about how do proper fractions, improper fractions, and mixed numbers work. I think I have a PowerPoint in here on simplifying fractions. If it'll load. In any case, it's there. And then a little bit on adding fractions with common denominators, or adding or subtracting fractions with common denominators. Just some notes that are here. It is not something that you have to turn in. There's not assignments here. These little things that say assignments here in the modules are just reminders that you are to log into MyLabs Plus to do your homework. But those 2 assignments on fractions are now live. And as always, if you have any problems with any of the homework problems, shoot me a message and remind, send me a message in Canvas inbox. Please, 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 please do not let your pride get in the way of you getting help. Go to Virtual Math World. You can see me during my Math World times or any of the other tutors, fantastic tutoring staff. Just make sure you check their times to see when they're available and what courses they teach. But don't put this off. Just get in there and let's start the semester off right. Does anybody have any questions about stuff we covered today, or if you have individual questions about things that, I don't know, you might be missing from last week, just hang back. But any questions at all? Let me go back to show you guys my face. Boom. Oh God, it's hideous. All right. Well, if there are no questions, or if you want to hang back to save your question for me once everybody's gone, you guys are free to go. Enjoy your week. I'll see you guys on Wednesday.
Thank you.
Thank
Bye.
you,
Have a good
sir.
day.
Thank you.